Wednesday, Friday classes end up being 10 to 11, 11 to 12. I've kind of split the hour from 10:30 to 11:30, but honestly, if you want to catch me at other times, come on by my office. My door's usually open. There shouldn't be an excuse, so I can't make your office hours. In terms of getting in touch with me, best way, catch me after class or during my office hours, particularly for questions involving organic chemistry where there are structures involved. It's very hard to communicate about technical matters by email, and I'm just honestly not too good at checking my email. Let's see, the other thing, the other people who are going to be very, very important to you in the class are the teaching assistants, Johnny Pham and Kim Lee, and I picked two of the best graduate students from my laboratory to serve as teaching assistants. Johnny and Kim, do you want to stand up? So Johnny and Kim are going to be handling the discussion sections, and so you'll get to know them in the various discussion sections for the course. They've set office hours on Wednesday and Monday, and they meet right in the area outside of my office, so you'll be able to meet with them. And I posted their email addresses here. So the textbook for the class is the Smith text, which you've been using. I won't go a whole heck of a lot into it. I think it's a pretty good book. I'm going to put emphasis on various parts in the lecture. It's a great book to read. You'll get a feeling for what I think are some of the most important aspects of the book. Some of the material I'll sort of funnel directly out, and I think they have a really good way of explaining things. Some of the things I'll pull from other notes of my own. You'll get a feeling from my perspective on the thing. Ultimately, what I want to be doing with this is sharing my perspective on this discipline with you, which I really love and am passionate about. Organic chemistry is so central to life and to all of its functions. Johnny and Kim are both earning their PhD in organic chemistry and are working on health-related problems. Johnny is working on how to understand in his research, how to understand and control protein aggregation in Alzheimer's disease using organic chemistry. Kim is working on protein interaction in cancer and in HIV transmission, again using organic chemistry. And the thinking that we're going to learn in this class is central to understanding all of life's processes and in terms of developing new medicines. All right, so the textbook for the class, as I said, is pretty good. By now, probably none of you are going to be doing this, but if you want to get the electron, if you're coming in, say, from having been in a different quarter elsewhere and you want to get the electronic version, that's available as well. Now, organic chemistry classes are really only a little piece of the picture. The biggest picture for organic chemistry, it's not reading the textbook, it's not just coming to class, that's sort of the basics. But the real part is active learning. And organic chemistry in particular, you learn by actively processing problems. One of my big laments in this section is I can't do what I've done in the honors class. The honors class has students get graded feedback from the TAs. It's also a much smaller class. And it's just so incredibly valuable when you're working and wrestling with a problem set and a deadline to have to actually work the problems yourself. And the other thing, of course, that's wonderful is deadlines. I hate them, but I love them for myself. I mean, it keeps me on focus. And this is a course, like in previous quarters, that have been pretty fast-paced. It's easy to fall behind in the class. And so what I've done is the next best thing to having Johnny and Kim grade homework assignments individually. And that is you're going to have electronic homework through Sapling Learning. How many of you have used this in previous quarters? So most of you are familiar with the system. This has been the first year I've adopted this system. I consider it to still be a work in progress. This is the first time. There's a lot of junk out there. I've been watching for years with the textbook companies coming up with junk that's multiple choice. This is the first point. I think it's getting close to thinking like organic chemistry. It's not perfect. It's a little clunkier on the implementation than I'd like, but it's a baseline. It's a starting point. On top of that, we're going to have problems that you work and present in the discussion section. And there are homework problems which, alas, a two-edged sword, have the answer key with them. So you can always check yourself. But I know there's this temptation when you're working problems to look at the problem, say, oh, I understand it, or I think I understand it, then look at the answer key. And that is such a short-circuiting to the learning process. And so I urge you, I beg you, if you want to master the material, don't do that. Actually write out the answer, commit, and then go ahead and look at the answer. And I know it's hard to have the result. So, all right. So you have the website for the course. And let's see, so we have discussion sections for the class. As I said, we're going to be working problems in most of these. I've made them match up to the chapters in the course. We're running through chapters 19 through 25, then we're jumping to carbohydrates in 27, and then the last week we'll do some special topics from amino acids and from some organic chemistry. And so I've matched up the discussion sections to them. You need to be enrolled in a discussion section. It's best to go to the one you're enrolled in, but if you can't make it to the one you're enrolled in, there are other discussion sections you can go to. It's a little confusing how I've juggled things because we missed Monday discussion section. We're going to hit the ground running with Tuesday. Discussion sections in the first half of the course are going to run Tuesday to Monday each week. Then at the midterm, we're going to switch. We'll have a block of discussion sections from Wednesday to Friday right after the midterm, which will be going over the midterm. I urge you to come to it. It's a great way to learn about things that you didn't understand. And then for the course after the midterm, our discussion sections will be running Monday to Friday. And if you're in the Memorial Day one, you'll just pick up one of the others. If that sounds confusing, don't worry, I've put a link here, and you can go ahead and see the schedule for discussion sections so you never miss out. So that's just on the syllabus website. Friday had 2 discussion sections that had very low enrollment, and so we closed those discussion sections. I urge you to come to I think it's the 12 to 12:30 on Friday. Instead, 12 to 12:30, but if that doesn't work with your schedule, just pick another discussion section. All right. This is the first time that I've taught this particular section, and so I've set up our schedule in advance. I think it's all going to work, but you should check the website just in case we make any changes in the scheduling. So I've set up all of our reading assignments for the year up here, and I've set up our first homework assignment and its deadline. And then others, I've set the deadlines, but I'll be getting the problems up there. The problems should be up about a week in advance. If you're not seeing the problems about a week in advance, send me an email and I'll let you know, let me know if maybe something went wrong with the posting.
Sorry, for the homework assignments, some of them say not to be submitted.
Great question. So the question is, for the homework assignments, some of them say not to be submitted. So the sapling ones, of course, you submit online. I would love to be able to see your paper written out homework. In fact, You would make me incredibly happy if you come to my office, if you ever don't understand something, and bring me a big sheet of sloppy, messy papers with pencil scrawl with all of your efforts on the homework. And if you come to my office, bring your notes. I want to know what you don't understand. I want to be able to help you. I want to see your homework. But as much as I would love for Johnny and Kim to be able to actually grade those homework, they can't. So, the second best thing to having homework that's actually due to hand in is problems from those textbook homework assignments are going to come back to you on the quizzes. So the quizzes, you're going to have seen all of the problems before. The quizzes are going to have problems that are taken directly from the discussion sections and from the Smith homework problems. The discussion section problems won't have answers. You won't be able to get them online. So you've got to go and visit the discussion sections to see the problems and to discuss them. All right, homework's always a conundrum, particularly in the context of the issue of academic honesty and grading homework. And I really thought deeply about this issue for homework because I see it as different from the exams. My heartfelt feeling for you on the homework is I want you to learn by doing the problems. Some people like to work problems alone. Some people like to work problems in groups. My primary feeling is learning. And it's not going to set up for that. If you get a problem wrong, it coaches you, you get a chance to do it over, there's just a small penalty. So for working in groups, my philosophy is it's okay to have real peer learning, to be learning from each other. What's not okay is to just be feeding a person the answers and then to be mindlessly typing them into Sackline. That's not learning, that's not teaching. If you're actually communicating and understanding your peer, you're learning how to communicate. You're better reinforcing the ideas in your mind. And your peer, in turn, is actually learning. And that's the atmosphere, if you work in groups, that I want to see on the homework problems. All right. So, got to come to the lecture section. You're going to miss things if you don't. I've set up this course on video. Videos for the course will be available if you have to miss the lecture, or better still, you want to review the lecture. You can download them. We're going to get them on YouTube, the OpenCourseWare site for UCI, and iTunes U, so there'll be lots of ways to access the material for review, but come to the class. All right, so quizzes. We have 6 quizzes. As I've said, the quizzes are going to come directly from the homework assignments and from the discussion section problems. The quizzes are on the dates that I posted here. We don't have makeup quizzes. We drop the lowest quiz. Any quiz that's missed counts as a 0. And I think that we drop the lowest quizzes. Quizzes are returned through the electronic thingamajiggy here. I think you're all familiar with electronic exam return? Yeah. Yeah, so you'll get your quizzes back through that. Quizzes count for 20% of the grade. The midterm exam, which is on Tuesday, May 8th, and covers chapters 19 to 22, is on, counts for 25% of the exam. The final exam is on June 12th and counts for 45% of the course, and the homeworks count for 10% of the course. There'll be a seating assignment chart for the midterm and for the final exam. I won't have seating assignments for the quizzes, although I'd appreciate it if you try to spread out and choose an empty seat without a neighbor if possible. You do need to bring a picture ID. A UCI ID is the best thing. A driver's license would be the alternative. for the midterm, before the final exam, we'll be passing them down the aisle, and the TAs will be matching your face with the ID and the exam, you know, the assigned seat. And during the exams, you need to have that. All right. All right, academic honesty. You all know what cheating is. Copying off your neighbor, getting materials in an inappropriate way. Don't do it. It is fatal in the course. You will get a 0 in the course, a note will go into your file, and you will not be able to go on with things that require this as a prerequisite. 2 students in my previous class of 1051 received a failing grade for cheating, and one friend of them who wasn't an enrolled student but colluded received a note in his file as well. So don't do it. All right. Cell phones. We all have them. We all love them. We check our email on them. We get text messages. Keep them away in class. Away, off, no buzzing. You can vibrate if it doesn't distract you. I find my own distracting if it vibrates, because it means, oh, there's something in my pocket that I now need to know on. Just turn it off. Don't tempt yourself with it. If you don't, if you're distracted by your cell phone, I will send you out to class. All right. By now you probably know about enrollment in these large classes. The professors don't handle any of that. It's done online and through the undergraduate office, and there's all the contact information. Tutoring, best place to get help. Me, Johnny, Kim, office hours, discussion section, their office hours coming by. If you want to get some help through tutoring, there's LARP. Chemistry also makes tutoring services available for free, and they'll have information that's posted. And then I already blasted you with an email, and I thought this was actually pretty cool what the chemistry department was offering. Rather than focusing on this particular homework or that particular homework, they were covering broad topics, and I thought, hey, that's pretty good. That's, of course, peer tutoring. So anyway, let's see if there's anything else that I want to talk about. I think that pretty much covers it. Oh yeah, I'll be giving you some software. I paid about $700 for this software. It's great for visualizing molecules, and they said I could give it to all my students in addition to using it for research, so it's really cool for looking at molecules. We'll use it later on to look at sugars and understand some of their stereochemistry. And so during one of the discussion sections, the TAs will be working with you to help teach you how to use that software. Who has a laptop computer or portable device in the class? So, good number of you. Bring those to that discussion section. That will be the week of, they will help you set up on your computer. That will be the week of April 17th through April 23rd, and we will remind you again. Alrighty. Well, I think that about covers it. So, questions on the syllabus or the course? So our discussions are running, the question is when the discussion starts. So we'll start on a Tuesday and run through Monday. So Tuesday, Wednesday, Thursday, Friday, Monday will be the same for the first half of the course. up through the midterm. And then after the midterm, we'll have 3 Wednesdays. So midterms on a Tuesday. So Wednesday, Thursday, Friday will be reviews of the midterm. And then we'll go on Monday to Friday schedule after the midterm. Oh, the quiz schedule. The quizzes, check the syllabus. I believe they are on Thursday, the first half of the quarter, and Tuesday, the second. All right, other questions? Well, I'm really enthusiastic about teaching this particular book. This is, in my opinion, the most exciting quarter of organic chemistry because we get to learn all the good stuff, all the stuff. You've now laid all this groundwork in place. You've learned about stereochemistry, you've learned about alkanes and alkenes and alcohols and texting on our cell phone. So, you've learned about all of this incredibly cool stuff. And now we come to what, in my opinion, is the richest, the most wonderful stuff in organic chemistry. And most of the class, 7 weeks, is going to focus on carbonyl chemistry. Broadly defined. We are going to start off with carboxylic acids. And the carboxylic acid family. We're then going to work on to aldehydes and to ketones. Aldehydes and ketones have just a fantastically rich chemistry. They have chemistry of reactivity at the carbonyl group. They have chemistry of reactivity at the adjacent carbon. Alpha-beta unsaturated carbonyl compounds have chemistry of reactivity of the alkene part of the molecule. Carboxylic acids. We're going to start off. Chapter 19 is kind of funny. It's sort of just a little, almost a throwaway chapter on carboxylic acids, just a taste of it. But carboxylic acids constitute a big and important family, and so we're going to learn about members of the family. We're going to learn about esters and amides. And so forth. And And then we're going to move on in about the 8th week of the course to talk about amines. And then we're going to spend the 9th week of the course talking about carbohydrates, sugars. And finally, if everything goes according to schedule, in the 10th week of the class, we'll have some selected topics from chapter 28. Chapter 28 is on amino acids, and so it's sort of a refrain of carboxylic acid chemistry and amine chemistry. We'll talk a little bit about peptides and their synthesis. And if everything goes according to plan, we'll spend maybe our last lecture talking about chapter 26 and some really cool organometallic chemistry that I want to show you. We won't have too much emphasis on this material, but there'll be one homework assignment from Sapling that's due to help reinforce that material. We won't go into painful or fantastic depth because you won't get a discussion section on it. is to plunge right into chapter 19, carboxylic acids. So carboxylic acids are really important compounds. You encounter them literally every day. One of the simplest carboxylic acids is acetic acid. You encounter that on your salad and salad dressing from vinegar. Get to taste your chemicals. You know that carboxylic acids are kind of tart, kind of sour, that some of them have some strong aromas to them. They're volatile. You encounter them also, perhaps in the morning, in your orange juice through citric acid. Citric acid is actually a tricarboxylic acid. Citric acid has 3 carboxylic acid groups, 2 on the end of the 5-carbon chain, and 1 off of the middle, along with a hydroxy group, so it's what we would call an alpha hydroxy acid. You might have heard of alpha hydroxy acids. Anyone? Face cream, stuff that you put on your face to go ahead and maybe do a peel or something for your skin. I don't know if anyone uses that sort of garbage. But you see it advertised in the cosmetic product with alpha hydroxy acid. Lactic acid in milk is another alpha hydroxy acid. Due to the inductive effect, they're a little stronger than regular carboxylic acid. The amino acids are also carboxylic acids. Your chapter gives a nice coverage of them, and as I said, we'll be coming back to them in chapter 28 in the last week. So I'll just draw one of these here. I will draw the simple amino acid alanine. I use the term alpha hydroxy acid. Alpha means the position next to the carboxylic acid. You'll also hear amino acids referred to as alpha amino acids. That's because the amino group is alpha on the position next to the carboxylic acid. All right, so carboxylic acids are important. And they're ubiquitous. And the defining feature of carboxylic acids is the carboxyl group. So we have a general structure. I'll kind of write out all of the lone pairs of electrons and all of the atoms here. In fact, let me be even more explicit. I have trouble getting in the habit. I'm so used to writing skeletal structures, but I will write all of the atoms here. So this is a carboxy group, the functional group that defines the carboxylic acid. The carboxy group is sometimes referred to as a carboxyl group. You will probably hear me refer to it both ways in this class. Now, you've already seen that I can write carboxylic acids in a number of ways. I wrote it as CO2H over here. So in addition to seeing structures explicitly spelled out like this, with or without the carbon, you'll see them written as RCO2H or RCOOH. These are all representations of the same thing. Compounds containing the carboxyl group fall into the broader family of carbonyl compounds. Which includes ketones and aldehydes and so forth. So this is the broader family. Much of the reactivity that we see in the carbonyl group of the ketones and aldehydes, which we'll be talking about later, you get in the reactivity of carboxylic acids and in their family members. So, one of the things that I think students get awfully caught up on is this whole issue of nomenclature. And it's really important to be able to understand the anatomy of something. In other words, to recognize when we look at a molecule like citric acid that I just had up, oh, there's a hydroxy group in the molecule. There's a carboxy group in the molecule. It contains a 5-carbon chain. It is that looking at a greater level of depth that, mind you, I will also point out, comes with drawing it, which is why I said writing out the homework, actively learning, is so important. And yet it is so easy to lose the forest from the trees in naming molecules and to start to say, oh my God, I've got to remember, do I alphabetize dimethyl under D for di or M for methyl? Do I put ethyl before methyl because it has an E or after because it's bigger? It's so easy to get caught up in that. And the fact that one can go on for pages and pages of nomenclature, that it's difficult to see the forest from the trees. So I'm going to talk about what I see as the forest from the trees on the nomenclature of carboxylates. You name them as the name of the alkane, chopping off the E, plus OIC acid. So very simple. If I have a carboxylic acid that has 6 carbons in it, 1, 2, 3, 4, 5, 6. The alkane that it would have been derived from is hexane, and so this molecule becomes hexanoic acid. The molecule that I drew on the blackboard before and said its common name is acetic acid is formally known as ethanoic acid. Got a great question by email last night. And the question was, how much do we have to know with carbon? Now, some acids have names that are so widely used that you'll probably never hear anyone referring to them by their systematic name. I doubt ethanoic acid would ever roll off of my tongue voluntarily, or at least outside of the context of a didactic situation, because everybody calls it acetic acid. Another one that's a perfect example where just about nobody would refer to it by the common name is this guy. Now, by the unpacked name, what's it? It's a 1-carbon acid. 1 carbon is methane. So its systematic name is methanoic acid. And yet you will invariably hear it referred to as formic acid. It gets its name from ants, because ants have formic acid in their bite. And if you distill, and indeed the way it was first isolated, might have been in a place much like UCI, which is loaded with ants. The first way they isolated formic acid was to throw ants in water and steam distill out the formic acid. And since ants in Latin are formis, they ended up calling the acid from ants formic acid. And of course, it's often the simplest compounds that have these historically driven common names because they were discovered so long ago. All right. So, the carboxylic acid is one of the highest ranking functional groups in naming. In other words, it ends up dictating the name of many compounds. So for example, if we have a carboxylic acid that also has a hydroxy group on it, we don't name it as the as the alcohol, we name it as the carboxylic acid. So this is 4-hydroxy butanoic acid. If you have a ketone group on the chain, like so, we would call this 3-oxobutanoic acid, again naming it after the 1, 2, 3, 4 carbon chain molecule, the 4-carbon chain acid. Like so many molecules, this has a common name. That common name happens to be acetoacetic acid. If you have 2 carboxylic acid groups at the ends of a chain, we call it a dioic acid, since there are 2. So this 6-carbon chain molecule is hexane dioic acid. You're going to encounter it in the discussion section this week. Hexane dioic acid. Hexane dioic acid is also referred to adipic acid. It's a component of nylon. Question?
Yeah, sorry. Is that dioic acid or dioic acid?
Dioic.
Oh, okay.
So it's HEXANEDIOC acid. Dioic. Pardon me. Thank you. DIOIC acid. Thank you. Good catch. Thanks. All right. The last sort of class that I'll just talk about in general is if you have benzene, then it's a benzoic acid. And so I'll just give you one last example. If we put a chlorine off of our benzene, this would be p-chloroparachlorobenzoic acid. Thoughts or questions?
Yeah, sorry. Do carboxylic acid make really good hydrogen bonds?
Do carboxylic acids make really good hydrogen bonds? Did I apply to a big class?
No.
Great question. They do indeed, and thank you so much for leading us into our next topic, which will be the physical properties of carboxylic acid. So carboxylic acids boil a little higher than you might expect for compounds of their size. Acetic acid is a little molecule. It just has 2 carbon atoms and a couple of oxygen atoms, and yet it's got a high boiling point. It has a boiling point of 118 degrees. And I borrowed this example from your textbook because I thought they did a really nice job of explaining things. If you look at a comparison, so it's a liquid, I think we would all expect something with a boiling point of 118 degrees to be a liquid, unless of course it were a solid that might melt below 118. If you compare it to a molecule about the same size, let's say butane, butane is a gas. It boils at 0. Molecules have boiling points above absolute 0 because there are forces that make them stick together. Liquid helium boils pretty darn close to absolute 0. It's 4 degrees Kelvin because helium is just the teeniest thing you can imagine. And the only thing that helium has are van der Waals interactions. Remember, induced dipole, spontaneous dipole, induced dipole interactions that make the molecules stick together. By the time you get up to hexane, to butane, of course you've got a lot more molecule and a lot more polarizability that can give rise to interaction. So butane has van der Waals interactions holding it together. It's about the same size, and yet the boiling point is a lot lower. If you go to a molecule like butanol, or let's go to propanol, for example, again, about the same size, about the same number of heavy atoms, about the same molecular weight as acetic acid. Butanol, propanol, has a boiling point of 97 degrees, so it's lower. 97, of course, these are all Celsius. So it's lower than acetic acid. You've got van der Waals interactions. You've got dipole-dipole interactions. In other words, you've got a dipole in the CO bond and in the OH bond, and that can make the molecules stick together. And you've got hydrogen bonding, because the OH groups can hydrogen bond other molecules. And so collectively, those interactions bring the boiling point of propanol way above, almost 100 degrees above the boiling point of butane. And yet, not as high as acetic acid. So hydrogen bonds are clearly worth something. How might you think about separating them from, say, the dipole-dipole component? Well, we could look at an example of a similar molecule that doesn't have any hydrogen bonding. So we could look at propanal. Propanal, again, is about the same molecular weight. It's got the same basic number of heavy atoms, 4 heavy atoms. It has a dipole in it, and yet it doesn't hydrogen bond. Its boiling point is 48. It's a liquid, just like propanol. And yet, without the hydrogen bonding, its boiling point is about 50 degrees lower. So you have van der Waals in dipole. So there's something really, really special about the hydrogen bonds in acetic acid and in carboxylic acids in general. Carboxylic acids love to hydrogen bond together because they can form a very nice hydrogen bonded dimer. In the hydrogen bonded dimer, you have one carboxylic acid facing another carboxylic acid, and the oxygen of one hydrogen bonds to the hydrogen of the other, and vice versa. And this makes the molecules stick together extra well. If you, in your laboratory course, ever run thin layer chromatography, TLC, on a carboxylic acid, you will see that typically they streak in the TLC. By streaking, I mean that they have a spot with a tail on it, like a comet, because at the front of the band on the TLC, as your solvent moves up the TLC, your sample is really concentrated, and it's hydrogen bonded to itself, so it doesn't hydrogen bond to the silica of the TLC plate and moves quickly up the plate. But at the tail, as it gets more dilute, you have less hydrogen bonded dimer, less of the molecule sticking to itself, and more of it available to stick to the silica gel of the TLC plate. And so it lags. The more it lags, the more diluted it becomes. The more diluted it becomes, the more monomer you have. The more monomer you have, the more it lags. So TLC-wise, you see very characteristic behavior of this. You see some really interesting features spectroscopically for carboxylic acid. So for example, in the infrared spectrum, you have an OH stretch at a characteristic position. It's really, really unusual. You see this very, very characteristic band from about 3,500 to 2,500 wave numbers. It's one of the ugliest features that you'll ever see in the IR spectrum. It's very broad. And the best way I can sketch it out would look something like this. If your IR spectrum sort of starts at 4,000 wave numbers, by about 3,500, you start to see this band come up and it's sort of misshapen, and then it kind of comes down at about 2,500. That's not hard carved stone. It usually obscures the CH stretches at about 3,000. And then as you come along in the carbonyl region at about 1,700 or 1,725, you'll also see the CO stretch, the carbonyl stretch. So let's say about 1,725 to 1,700 wave numbers. So really, really characteristic, just staring you in the face when you look at these. So NMR and IR spectra also have characteristic features of carboxylic acid. And a lot of this, the best way, you'll get to see some of these compounds in the lab class if you haven't already. The best way is to actually see spectra. Question?
About the IR spectra, I read that if the carboxylic acid is more concentrated, you don't get such a broad peak in the 2,500 or 3,500.
It's still pretty ugly. And so the question that's being asked is about concentration. And if you run it, concentrated would be, say, the liquid sandwiched between two salt plates would be typical. Or if it's a solid, in a potassium bromide pellet. And those tend to be really ugly in my experience. In solution, I haven't looked personally recently. I would think, if anything, you'd possibly very dilute see a little more monomer, which would be more well behaved. So I'm not sure that that's true, but if you see an example, I'd love to see what you're reading in there. It's the other thing that's interesting in the IR spectrum. Some of it depends on how big the molecule is. After all, if you've got a small carboxylic acid like butanoic acid or acetic acid, that molecule has a ton of carboxyl compared to other stuff. So when you're sandwiching a drop of acetic acid between two salt plates, there's a ton of carboxyl groups. If you had a molecule with 20 carbons in there and just one carboxyl group, you'd see a much smaller stretch for the carboxyl group. So what I'm saying here, and for that spectrum, is sort of characteristic of a smaller molecule. For like a really big molecule, like a steroid, like a cholesterol molecule, the carboxylic acid peak will be smaller and a little bit less obvious. But they're still really, really obvious. Good question. Other questions?
So how can we differentiate a carboxylic peak from just an alcohol peak?
Ah, great question. Carboxylic acid from just an alcohol peak. So typically an alcohol peak, and again I'll refer to one concentrated, kind of picks up at about 3,500 and kind of comes down by about 3,000. So this would be a typical alcohol. And you'd see it more sort of centered at 3,300. Whereas the carboxyl is pretty featureless. It may have some small features over here or over here. And it's just sort of this blob that encompasses the CH region at about 3,000.
Oh, sorry. One more question. So how can we see the CH peaks in the carboxyl?
You may not. The question is, how do we see the CH peaks? And the answer is, you might not see them, but guess what? These days, in organic chemistry, there are so many ways to tell if a molecule has CHs in it, for example, NMR spectroscopy, that in general, it's less important. And in a scientific journal called Journal of Organic Chemistry, back many years ago, when IR was the primary way of describing molecules, you were supposed to describe every band in the spectrum and list like 20 or 30 peaks. Nowadays, the instructions, since there are so many good ways of looking at molecules, the instructions are list the main peaks associated with functional groups. So these days, if Johnny or Kim prepared a carboxylic acid and described it in the Journal of Organic Chemistry or in a laboratory report, they would probably say 3,500 to 2,500 wave numbers, broad peak, and 17, let's say 10 wave numbers, another peak. So you may not see them. But in the NMR spectrum, you of course get to see lots and lots of hydrogens. The carboxyl hydrogen, ironically, you don't always see. Generally, it's about at 10 to 13 ppm. Your textbook says 10 to 12. Either of those is fine. Often it's broad. Its position depends a little bit on the solvent, if you're looking at it in chloroform, if you're looking at it in dimethyl sulfoxide. And sometimes you actually won't see it. Your textbook and I would never give you an example of an NMR spectrum where you didn't see the carboxylic acid OH. But if Johnny or Kim went into the laboratory and prepared a carboxylic acid and were trying to determine if it were carboxylic acid and took an NMR spectrum in chloroform and said, I don't see the carboxyl OH, even though it looks like a carboxylic acid in the infrared spectrum, I don't know if I have a carboxylic acid. I'd say, you know, sometimes you don't see the OH because it can be very broad due to exchange with water. Why don't you go back and run the NMR in a different solvent like dimethyl sulfoxide and you try and come back and say, I see it. But your textbook would never give you that much reality, or I wouldn't, because it's way beyond the scope of this book. But that's the reality. Now, the other thing is, okay, what do you think about when you think about the hydrogens? The carboxyl group is electron withdrawing inductively. And so the CH that's next to a carboxylic acid generally appears at about 2 to 3 ppm. The textbook says 2 to 2.5. Either is fine. If it's a methyl group, it'll be at about 2. If it's a methylene, a CH2 group, it'll be about 2.5. If it's a methine group, a CH group, it'll be about 3. And if there are other electron withdrawing groups, it'll be further downfield. The NMR spectrum, the carbon-13 NMR of carboxylic acids, your carboxyl carbon generally appears at about 170 to 180 ppm. That general region of about 170 and further downfield is generally referred to as the carbonyl region. So generally, carbonyl compounds are generally about 170 to 220. Your textbook said for carboxylic acids 170 to 210, but they were really trying to encompass all of the carbonyl region. Generally, it'd be about 170 or 180 ppm. I'm going to write in general here. So, carboxylic acids, carboxyl group of carboxylic acids is in a high oxidation. In fact, They are the highest oxidation state of any organic compound, with the exception of things that are in the carbon dioxide oxidation state. So if you in general have a carboxylic acid, like acetic acid or hexanoic acid or benzoic acid, the oxidation state is +3 for the carbon. In formic acid, if you count your oxidation state, it's +2. But what that immediately tells us is they're generally synthesized by oxidation reactions, because in general, a lot of organic compounds you encounter have carbon in lower oxidation states. So alcohols, for example, depending on the substitution, will have oxidation state of, if it's a primary alcohol, -1. If it's secondary, it'll be 1 different. And so primary alcohols can be converted to carboxylic acids by oxidation. And you've already encountered oxidation reactions in the 51B course. So for example, with chromium-6 reagents, say e.g. with chromium Vi. So what I mean is potassium dichromate and sulfuric acid, or sodium dichromate and sulfuric acid, or chromium trioxide and sulfuric acid. They're all about the same in their reactivity. There are other oxidizing agents. In general, chromium-6 is a really bad actor. It's carcinogenic, it's toxic. In general, organic chemists try to use safer oxidizing reagents these days, ones that are more environmentally friendly and don't generate waste. So other sorts of oxidation systems that get used involve things like bleach, sodium hypochlorite, and various catalysts. Anyway, the general gist is there are many oxidation reactions that can synthesize the carboxylic acid group. So for example, you're also familiar with oxidative cleavage. Of alkynes with ozone. That's a little bit of an oddball in some way, because alkynes aren't that commonly occurring. Alkenes are a lot more common. So I also included in the example in this week's discussion section alkenes, and you'll see a reagent system for the oxidative cleavage of alkenes. Your textbook provides a nice review, and so you'll also see in your textbook oxidation of aromatic compounds. With a benzylic CH group. As another example. So these are all things that you've encountered in your previous course. And in that case, you'll see, for example, potassium permanganate, KMnO4, as a reagent. Carboxylic acid implies carboxylic acids are acidic. They're not strong acids like sulfuric acid, like battery acid or hydrochloric acid, Those acids, if you dissolve them in water, completely ionize. A 1 molar solution of sulfuric acid is pKa, or 1 molar solution of hydrochloric acid is pKa of 0. Is pH, pardon, 0. It's a very strong acid. If you splash it in your eye, it's going to cause real damage. Vinegar is a weak acid. Vinegar or acetic acid is a weak acid. It's a 5% solution, which is close to 1 molar. If you splash vinegar in your eye, it's going to hurt, but you'll wash your eye out. You're not going to be blind or need to go to the emergency room. Weak acids and strong acids, of course, react with strong bases. So, for example, acetic acid reacts with hydroxide anion to give you acetate anion in water. And I've sort of focused here on the ions. You can't just buy or find a bottle of ions. If you go to the stockroom and you say, give me some hydroxide, they're going to say, well, I can't just give you any hydroxide. We've got to have a particular hydroxide. I can give you sodium hydroxide, I can give you potassium hydroxide, I can give you calcium hydroxide, but you can't get hydroxide ions just to sit with each other without metal counterions. They push each other apart. And so we could write a real balanced chemical equation for, say, acetic acid plus sodium hydroxide goes to sodium acetate, CH3CO2, I'll write it as minus NH plus. And, you know, be a good person. Organic chemists are not good people. We're horrible about balancing equations, but now I'll be a good person and balance my equation. So we get sodium acetate in water.
Spencer?
Yes?
Oh, sorry. For the sodium acetate, shouldn't it be CH3CO2 minus?
CH3CO2 minus. Thank you. I want you in the front row every class. And I want everyone else to help out with this.
Yes.
So, I haven't written an equilibrium there because that reaction just lies so bloody far to the right that for all intents and purposes, if I throw sodium hydroxide, 1 mole of sodium hydroxide, together with a mole of acetic acid, there's no acetic acid left. I've got a mole of sodium acetate. That equilibrium lies fantastically far away. Acetic acid has a pKa, so an indicator of acidity is pKa. The pKa of acetic acid is 4.76. That's typical of a weak acid. The strong acid, like sulfuric acid, is negative. Hydronium ion is negative, I believe, 1.7. In this equilibrium, water is acting as a base. Hydroxide is acting as a base. Water is the conjugate acid. We often compare equilibria by comparing the conjugate acid on the two sides of the equation. Water has a pKa of 15.7, acting as an acid. In other words, it's a much weaker acid, much weaker acid than acetic acid. That equilibrium lies to the way to the right. So far to the right that we barely consider it as an equilibrium. Organic chemists often think about water and alcohols together. They're kind of in the same family. They both have hydroxyl groups. They have many similar properties. The pKa of alcohols is very similar to the pKa of water. Alcohols are about, if you want to keep one number in your head, about 17. If you can't keep one number, just say, oh, they're about the same as water and call them both 16. So these are weaker acids. Their conjugate base is RO minus or OH minus. And so if we think about why they're weaker acids, one model in which to understand this is when we look at acetate anion, we can spread that negative charge around. There isn't a negative charge on one oxygen and a neutral charge on the other. There isn't a double bond to one oxygen and a single bond to the other. It's sort of half and half. There are two resonance structures that are equivalent that together represent a more complete picture of the structure of the anion. We can say that the negative charge is stabilized by resonance. And that special stabilization that doesn't occur in hydroxide anion or in alkoxide anion makes this a weaker base, makes acetic acid a stronger acid than water or than an alcohol. Organic chemists aren't big calculators. Organic chemists are big estimators. We tend to think about things in sweeping terms. So when you're taking general chemistry, you're typically focusing on calculating in detail positions of equilibrium. When you're thinking about organic chemistry, often you're thinking about acid-base reactions and asking, where does this equilibrium lie? Does it lie in the middle? Does it lie to the right? Does it lie way to the right? Does it lie way to the left? Does it lie a little bit? And that's how I like to use pKa's in my thinking. So when I think about equilibrium in an acid-base reaction, I sort of think about broad estimates in terms of pKa, and I'm going to write an equation. I hate to write equations because that's not how I think, but I'll show you how I get to my thinking. So the equilibrium constant is 10 to the delta pKa. So what do I mean? I mean, if you have an acid, RCOOH, and its pKa is about 5, see, I'm not even going to worry about extra digits here, because basically I'm thinking in broad terms. Carboxylic acids have pKa of 4 or 5. And I have a base, like alkoxide or hydroxide, and I have an equilibrium. I've already said this equilibrium lies way to the right, and I'm so far to the right, I'm not even bothering to think about why it's where it is. So here's my equilibrium, and the pKa of my alcohol, or my hydroxide, is 17. My estimate, the thing that's going on in the back of my head, is, oh, KEQ is equal to 10 to the 17 minus 5 is 10 to the 12th. That equilibrium is so far to the right. It's hardly an equilibrium. It's just there. It's just reacted. You know, 10 to the 10th is a big number, right? If it's 10 to the 1, 10 to the 2, maybe even 10 to the 5, even maybe sort of up a little bit above that, like 10 to the 8th, you could say, okay, there's kind of sort of an equilibrium. But this is way, way, way to the right, which is why I didn't even bother doing equilibrium error. All right. So most carboxylic acids are pKa of 4 or 5. We saw it with acetic acid, 4.76. Benzoic acid's a little bit more acidic. But sometimes you have big effects. Sometimes you have big effects that lead to inductive stabilization of the conjugate base. And that's going to lead to a stronger acid. So, as I said, typical carboxylic acid is 4 to 5. But if you take something like trifluoroacetic acid, trifluoroacetic acid has a pKa of 0.23. Johnny and Kim work with trifluoroacetic acid all the time in the laboratory. They use it as a relatively strong acid, sort of right on that equilibrium between strong, meaning you pour it into water and it all ionizes, and weak, meaning it doesn't ionize a lot. It ionizes a lot, but not completely. If you get it in your eyes, there, you should worry about it. If you get it on your skin, there, you should worry about it. What's going on? Those fluorines are super, super electron withdrawing, and we've got 3 of them. And so they all have these dipoles pulling negative charge away from the conjugate base, stabilizing the conjugate base. And so we get 5 orders of magnitude more acidic than a regular carboxylic acid. If you put fewer electron withdrawing groups, like 1 or 2 fluorines, you get less acidity. If you go ahead and you move your halogens down the chain, like 4-chlorobutanoic acid versus chlorobutanoic acid, out 2-chlorobutanoic acid, they're both more acidic than butanoic acid, but 4-chloroacetic acid, butanoic acid is a little more acidic, whereas 2-chloro is a good bit more. And you get the same effect. I'll give you one last example to close here. You get the same type of effects with benzoic acid. And you can think of this in terms of the inductive effect that we've learned. So benzoic acid has a pKa of 4.19. If you take para-nitrobenzoic acid, you can have inductive and resonance effects pulling electron density away from the carboxyl group, and its pKa is 3.11. So you get effects there. All right, I think that wraps it up for today.